Okay, this video is on electromagnetic induction. What we have here is two coils. Initially it's very simple. It's just a piece of copper wire and we put a current through it and it creates a magnetic field. A changing magnetic field in time creates a EMF on the opposing conductor over here. It's more complicated than that. What we've got to realize is that this is a waveguide. This is it's a resonant cavity. Basically, the copper wire is insulated. The copper wire has a resonance where the electrons can be put in one end and they can be found to be a resonant with high amplitude at a specific frequency without having this wire connected at all. It's one of my favorite experiments. So basically what's going on here is the coil can act as an antenna, and that's what Don Smith said as well. The coils are antennas. So we have a frequency where this coil can be resonant, we have a frequency where this coil can be resonant, and at these resonant frequencies the impedance of the coil becomes zero. We have a wire resistance which is still there, but at resonance XC and XL are equal, and the impedance thus becomes zero, or it drops right down. So reduced impedance basically. Now again, the path from this terminal here, the path is a resonant cavity because of the insulated copper wire. The electrons can only travel down the wire, and at resonance they travel down the wire with no impedance, or with very little impedance. When they get to the end of the wire, they reflect because there's no connection here, so this would be no connection. So say for example we had this probe here, or this connection here is our input. We have a resonant frequency that's been applied to the coil. The coil is in resonance, it's a resonant cavity. The electrons flow all the way up to this end of the wire. They see a high impedance, which is no connection, and then they come back down the wire at that resonant frequency. So as much comes up as much comes back again. There are little, very small losses, but it's minimal. Anyway, so we've got to think about these coils as resonant cavities. Very important. Very important. It truly is. Okay, so in electromagnetic induction, it's a very simple process, but people seem to mystify it. People don't seem to understand it. The time rate of change of the current, okay, it's not the voltage, it's the current. So the time rate of change of the current in this coil creates a magnetic field. The magnetic field changing in time creates an EMF, which is the voltage on this coil. Okay, so current on this coil creates voltage on this coil. Now if this coil is loaded and we have a load on it, then this coil then carries a current. If this coil is not loaded, it doesn't carry a current. There's no current flowing in the coil. Okay, and when there's current flowing in the coil, there's a magnetic field. So the magnetic field then opposes the primary. The primary impedance goes down, and then the primary current goes up. Thus we use more power on the input coil to keep the electrons flowing. Okay, you've got to remember this is opposing magnetic fields, so as soon as the magnetic fields oppose, we keep the electrons flowing. Okay, if we were to drop the magnetic field instantly from this coil, the current would drop instantly as well. Okay, so we have to support the magnetic fields. The magnetic fields have to be opposing, and we have to support them to pump electrons. We're pumping electrons. Okay, electromagnetic induction is pumping the electrons. Okay, we understand electromagnetic induction today as a symmetrical process. So it basically means we have one action, one reaction, and that's not true. It's not true. We need to think asymmetrically. We need to think action, reaction. We'd have a third coil over here, and that would be counter reaction. So we have a magnetic field changing in time. When this coil is loaded, we have a magnetic field also changing in time, which opposes the primary action. Okay, and this coil here, because it's now got a magnetic field changing in time, we can then have this coil become a primary for the third coil. But we've got to get our timing right, and we also have to probably use something like delayed conduction, which I've also been through on my website. Okay, so I really want to stress these points. Electromagnetic induction it's not new, it's 200 years old. We only understand a little bit of it. There's much more to it. Okay, we do have a reasonably good grasp of it, but we've only thought about it symmetrically. We've not thought about it asymmetrically. There's much more to it. So what I'm going to do is quickly show you that it's not magic, and yes, that it does work. So we've got scope probes over there. Scope probes are going to measure the input current and voltage. That item. Okay, so our coils again, and yes, we do have light. Okay, electromagnetic induction. It's something that I couldn't recommend highly enough. Please do some simple experiments. Please get on the bench and do some simple experiments like this to prove that electromagnetic induction, first of all, works. It's simple. It's right there in front of us, and second, that we can do very much more with it. Okay, it's a 200 years old nearly, but it's still really in its infancy. Okay, so mutual coupling coefficient. If we move this coil away, our light reduces. Okay, so the changing magnetic field from this coil is not having so much of an effect on that coil. Okay, so the further away we move the coil, the less light we get. If we move it closer, okay, light gets stronger. We have a better coupling between the two coils. Okay, now if the secondary coil is wound on top of the primary coil, that's called unity coupling. Okay, and that's when there's a maximum coupling between the primary coil and the secondary coil. They call it unity coupling, and it's wound over top of the primary coil. Okay, now it's important to note that when we have a closed magnetic core, that there's no flux that's outside the core. Nearly all of the flux is contained inside the core itself. So no flux touches the coil itself. Okay, it's an important note. It's something really important to note. Okay, all the flux is inside the core. No flux at all touches the coil. It's what's called the magnetic A vector potential. Okay, and as the magnetic field is changing in the core, as the magnetic field is changing inside the core, there's an electric field that surrounds the core that's left behind. That's part of the magnetic A vector potential. They call it A and phi. Phi is the flux. Again, the flux is contained inside the core. And again, if we reduce the coupling, okay, so we have maximum coupling in this particular setup when they are close together. Okay, coupling coefficient K is how they measure it. It's normally a factor between 0 and 1, 1 being maximum coupling, and they would say 1 if the secondary is on top of the primary. So that's unity coupling. Okay, Very quickly, input voltage and input current. Input voltage is the red one, input current is the yellow one. The input current is, you can tell by the peaks, it's nearly a sort of a triangle wave. You can tell that the core is nearly saturating because of that shape. If it wasn't saturating, we would have a standard sinusoidal wave. So we're nearly in saturation at the moment. By going into saturation, we nearly have a going close to and then back out again. We have a resonant frequency on that coil, on the input coil, okay, which is not super important. I mean, that's something that's just easy to get. It's just something I wanted to show. So the amplifier is driving that coil at a pretty good efficiency. So that means most of the power that's going into the coil is then coming back out of the coil again. If we have a 90 degrees phase shift, which is nearly 90 degrees there now, if not 90, then we have a very efficient coil. The coil is running with no power. All power going into the coil to create a magnetic field, then comes out of the coil again, back out. Okay, so again, electromagnetic induction, it truly does work. It's not rocket science. It's something that people need to get onto the bench and do. Okay, we have an input over here to the coil, back out to our measurement bridge, and then it's back down to our amplifier, which is under the bench. It's just an audio amplifier. You've seen it before, driven by my PSU up here. Okay, again, the coupling, okay, the amount of magnetic field that this coil sees changing in time, okay, because this over here is a magnetic field. The current flowing through the wire, okay, is what creates the magnetic field, and it's changing in time. So as this coil changes in time, this coil sees the change and it produces a voltage. That's what they call a generator, okay, quote unquote generator. And if it's coupled nice and closely, then we get a better EMF. So again, I just want to reiterate, current changing on this coil creates voltage on this coil, not current. It creates voltage. Okay, so again, current changing in time creates a voltage on the secondary. When the secondary is loaded, Ohm's law predicts the current. Okay, so the resistance of the coil, the resistance of the load, then determines the magnetic field, okay, the current that will flow. Now, if there's no load on the coil, no current, but we still generate an EMF. So the EMF is still generated. So the changing magnetic field, which is the current on this coil, creates a voltage on this coil. If this coil is loaded, it then creates a magnetic field because there's a flow of current in this coil, and the flow of current in this coil opposes the change on this coil. Okay, so we have a current flow, which you can imagine just water in a pipe in a big circle, and then we have a current flow in this coil, water in a pipe in a big circle. They oppose each other, so the magnetic fields want to push apart depending on the part of the cycle, or pull together depending on the part of the cycle that we're in. Okay, I want to add the mass that we're looking at. The mass, okay, the copper wire, conductive copper wire, the mass itself is made up of subatomic particles, okay, charge, electrons, protons, neutrons, which are negative, which are not charged. They have no charge, they have no magnetic field. It's just a neutral particle. Okay, it's made up entirely of subatomic particles. Okay, and this is something that we forget. There's enough charge in that copper coil probably to light a small city for many years. Okay, if we were to take all the charge out of that coil, all the charge being all the electrons, okay, all the other charge that may be present as well, which is speculative. All the charge in that coil, it's a reservoir of charge, it's a reservoir of energy. But if we take the charge out, the copper will still be there. The copper doesn't change. It doesn't change as we pull electrons out of it, free electrons, and that's something else. As we're freeing electrons, our job is to free the electrons from the binding forces of the atom inside the copper, okay, which is inside the insulation. Okay, so it's something that we've got to think about. It's something that we've really got to concentrate on, and it's something that we really have to focus down on a subatomic level. What are we doing? We're first of all freeing the charge from the subatomic. Okay, and then as the charge is freed, then what we'll want to try and do is then get it moving. Okay, we've got to accelerate the charge down the wire. Okay, and we've got to do it at a frequency that it likes to do it. Alright, it's part of our job. So I just want to say again, I urge everybody that's interested in this, get on the bench. You don't have to have anything flash. Start with the basic stuff. Just start with small amplifier, a few small coils, and look for the effects. Okay, asymmetrical electromagnetic induction. It's not new. There's lots of devices out there in the past that have used it. Okay, so we are copying off other people, but we do need to learn something that effectively is new to the scientific community. Okay, so primary coil, secondary coil, tertiary coil. 3 is the magic number, literally. Okay, we need to learn how to get the primary to induce a voltage, load the voltage to make a current that changes in time. This current that changes in time induces a voltage, and therefore a current when loaded on the tertiary coil, not shown, that then will change in time. So this coil has a magnetic field changing in time. This coil, because it's loaded, has a magnetic field changing in time which opposes the primary. This coil here induces an EMF, which then is loaded on the tertiary coil, which opposes the primary, but assists is addition to the primary coil over here. Okay. Alright, just want to make a short video. Just noticed there seems to still be a huge amount of confusion, or at least a misunderstanding about a very, very simple process. Okay, electromagnetic induction is not a new thing, so I sort of do really expect people to do the experiments and get a good grasp of it, because it is a very, very important aspect to what we are doing. Alright, thanks guys. I just want to say, if this video did help you, please consider a donation. It helps us out, helps keeps the wheels spinning on our effort, and I just want to say thanks to everybody again.